Hi everyone, it's time we kicked off my presentation. I'll be talking about the control flow hijacking in the Linux kernel. This is a follow-up of the previous presentation. I'm going to give you more details on how to attack the kernel, and I'll be talking about how to fend off such attacks. Hold on a second. For starters, let me introduce myself. My name is Valery. I'm a Linux kernel researcher in Positive Technologies. I've been contributing to various open source projects, and I have my own projects. I'll be talking about them later. The agenda is on the screen. First, I will share with you some basic things for people who are not experts on that. Then I'll speak on the shellcode, what it is. I'll give you a vulnerable bin example that can be attacked, and then we'll be talking about more complicated things. I will demonstrate to you the open source attack stand. And jumping ahead, I might say that using the stand, you can test the things I'll be talking about at home or even now. And then I'll show you the vulnerable kernel mode. Let's start with the basic things. The shellcode is what we call something that gives you a shell, and oftentimes it's just a system executive. And exec VE is /bin /sh followed by 2 zeros. All the other, well, this is a hyperlink for x64 syscall sh. You can use this hyperlink to get additional information. And when the control flow is hijacked, you need to follow some instructions, right? So this is an example that I programmed on an assembler. If you never used an assembler, don't worry about it, because we'll only be using these 5 instructions. So the first one launches the number 59 into the assembler. This is just a system exec VE number. It has nothing to do with logic. And as the first argument, we upload the location in the binary code, and then we add 2 zeros. Then we put it in the library, assemble it, and this is the way the shellcode works. I use the radar to look through it. It looks exactly the same way, and it demonstrated the 16-bit code. Nothing much changed. And, well, actually, let me show you why we decided to disassemble it. If you use the common copy to share the shellcode that you created, that you assembled, I call it shellcode raw, then you can try and do something with it. And for starters, this is a vulnerable code in the user space. And, well, the most important thing shown on this slide is the code that you can name with your own name. And, well, you can try and type in your own name, but the most important thing happens here. It's a polite bin, so it discerns between ordinary users and admins. If it's an admin, then it says hi. But if it's just a ordinary user, then it doesn't do anything. But the coder in this particular case made an error because the hello function, which is highlighted and which rules the highs and goodbyes, first states the name and then the index of the function that is going to use to bid goodbye to someone. And if it's not an admin, then the arguments were misused. On the face of it, it's nothing much, but let's try to compile it in the GCC, and we'll see the errors, the warnings, and then in the executable stack we're going to see it. So this error is visible in the terminal if you just assemble the code and if you try to execute the binary file. If you're not an admin, then you get a segmentation fault. How can we exploit it? First and foremost, it works like this. The vulnerable function features a name and then the pointer, which is by admin. The first one is the RDI entry, and the RSI is the second pointer function by admin. But if it's not in the admin, then the name and the pointer are replaced, and that's why you get the segmentation fault. And shown on this screen, well, you can see it better on this screen, and initially it displayed the name and then tried to revoke the function, but then in the compiled code we use this tricky pipeline to feed the raw bytes that I talked to you about. I have a fish system, and in a bash system it's way easier because you can use these quotation marks to execute the function, and you get the real shell. Let's imagine that this was something accessible from the outside. It could be exploited to get remote access to a specific object. As for what's next, this is an online meme. Well, if you have ever tried to debug something or fine-tune even user space rather than kernels, you probably saw an image like that. Binary debugging is a very complex. Bin debugging is a complex thing because everything crashes all the time, nothing operates well, and you need to do something about it. So during this project, I came up with an open source stand. It's very simple. All you need to do is clone your project, launch one-page script, and it's done. The stand assembles from the source code. See that smop.c and smip.c is exploited, so everything is assembled from the source code and is fed into the NitroFS. It's less than 20 megabytes, so make sure you test it. Moreover, since I provide the open source, you can try and modify the exploits, try to debug them, try to use all the techniques that I will go over during this presentation. You can also try and do something new. For instance, add Linux kernel defenses that I am not going to be talking about, and even write a new code or contribute to the project. Let's move on to the main part of my presentation, which is the Linux control flow. Hijacking will start with the basics when all the defenses are down, and I'll start with fundamentals, and then we will complicate things as we go. The slide shows the vulnerable kernel module, and the most important thing that we can see here is the vulnerability that I'm gonna be talking about.
Кроме большого комментария, здесь есть char-буфер на 32 байта.
We have a char buffer for 32 bytes, and the memset is filled with zeros. Following that, you get the copy from user line. Everything seems to be fine, but The headset says the size T count, which means that when you feed data from the user space to the kernel space, it's the user who controls the data set. Therefore, for instance, if there are 10 bytes in a line, 11 bytes would be transferred. If it's 30, then the 31 bytes are fed into the kernel space. It's not the entire module, of course. It's just the processing function, because it's the vulnerable function. Don't think that the entire module takes just 5 lines. In fact, since count is user-controlled, then the very first thing that comes to mind is just transfer more than you have in a buffer. And there are several things that I wanted to touch and highlight from the get-go. This is a diagram to demonstrate how it happens in memory, because we are in the stack, right? So the RBB register is transparent here because on my PC it was non-existent, and the compiler just streamlined my code. Since I just had a buffer in the stack, I decided against installing the RBB. I switched off the defense mechanism because I didn't have any leaks, and I can only try and write something in the kernel because I don't have any data leaks, so that's why I switched this off. I switched the canary off. So this is the way it looks. I went over everything. So we use our 32-byte buffer and try and write something over. So let's say I have 40 bytes as opposed to 32. So it's plus the terminate byte, it's 41 bytes. The error log is shown here on the screen, and highlighted in bold is the RIP changed registry. Now it contains 0x45, 45, 45, and so on and so forth. This is the ASCII code of the E. And right after the buffer, what you see is the return address. Therefore, if you send more info than the buffer capacity, then the kernel stack is overflows. So it fills the space with some values, some user-controlled values. This is what we call stack smashing. And since we control the data, it's quantity, and since we know that the return address is right after, we can hijack the control flow. The only thing you need to do is write the shellcode and the payload that will execute the shellcode. And this is the way the kernel works when nothing bad happens, and a user can use the module when you transfer less than 32 bytes. The vulnerable function returns the data, and the data is copied. However, if we try to hijack the control flow, well, the design might look the following way. We overflow the function, and since we control the raised return index, we can invoke a function in the user space that will give us access to the root directory, hypothetically speaking. Inside the function, we can revoke kernel commit crash, and I'll be talking about that later on. And we can implement it in the following way. As you can see, this code is longer, but don't worry. In Rx, we sum up the kernel crate, and for the prepare kernel crate, we use 0 and from the RDI register to invoke the function. The prepare kernel cred is used as a commit cred parameter, and we move the rx value to the RDI. Then I had to hard code some of the things, so I returned the RSP register to where it usually is. And this is it. I just restored the way it was. As for the shellcode, it was quite simple to do. I used the PC box, which instead of compiling all utilities, we use just one. And the PC box /bin//sh use it as a hyperlink to the PC box. And this is just a binary bin1 busybox. And
но какие-то сакральные знания в интернете, если что, это есть.
It's common knowledge. You can find it online without any problems. And well, these are the screenshots for the sake of the demo, but I decided to run a live demo. So right now we're in my project that I talked to you about. Well, you can test it at your leisure. I talked to you about that a couple of a dozen slide backs when we launched the bash script. The system asks about the protection means, and I specify SMEP, SMAP.
rootfs сжалась, мы...
The rootfs was compressed. We get access to the virtual machine, and we can do whatever we please. For instance, write down the ID just to make sure that the system understands that we are just an ordinary user.
Попробуем, например, сделать вот так как-нибудь. Ну, поймем, что...
So let's try this, and it's quite clear that we don't have the privileges to manage anything in the system. So we're going to use the exploit I described to you previously. Everything works. We double-check the ID.
Получим флаг. Все как...
And we get a flag just like in CTFs. And then you can go to the Control-D and do whatever you want. Everything works, and then we leave the kernel and go back. In a nutshell, this is it. The next thing I'd like to talk about is the SMEP. This is a kernel protection means that can be a huge obstacle. For instance, if you try to use the previous exploit with the SMEP supervisor mode execution and prevention on, then the kernel will not grant you access, and it'll say unable to execute user space code. Which means that the code that you're trying to execute is in the user space, and it can't be done like that. So you might think that everything was in vain because the kernel can now be thrown out into the waste bucket, but actually we can use the knowledge to adapt for the new environment. So what we're going to do is we're going to try and identify the gadgets. I'm going to give you more details on that in the follow-up slides. These are the manuals that you will see in the kernel space, and since the kernel is a compiled binary code, we can just disassemble it and use these gadgets either from the debugger or the bin file. And you can use the rough gadget utility. It has a million starts on GitHub, so make sure you download it. It allows us to identify parts of kernel code that we can use. the call sims or the debugging symbols. You can use a debugger or any other way to find them. And the last thing that you need to do to bypass SMEP is the stack pivoting. Stack pivoting is a technique when you replace the RSP register with any value which is convenient for you. And by convenience, I mean reading or writing some memory block. And it's quite clear that this memory block should be in the user space. Therefore, we replace the RSP register with 0x83 and 4 zeros. But before that, we just test whether we can read and write in that memory block. So the exploit looks in a different way. As you can see, the structure is basically the same, but we now assembled the ROP chain, which allows us to bypass the SMEP. And I used the stack pivoting with the help of the gadget shown on the screen. On the previous slide, I demonstrated the way the RSP register can be replaced with this particular value. And the CPU just starts executing the manuals in our stack. And you can unmap it this way and input the next value. This is another live demo.
Задайте вопрос в конце толка, я обязательно расскажу.
I will definitely answer that question at the very end. So we activate SMEP.
Это очень хороший вопрос.
But that was a great question, by the way.
Проверим наш ID.
Let's check our ID.
Выполним exploit.
We execute the exploit and everything works. The IDA is different and we can do the cat root flag. Everything works perfectly. The next kernel protection means I'm going to bypass is the SMAP. And it's more powerful than the SMEP. When I first saw this log, I did not understand anything because it doesn't say what went wrong. The kernel says double fault, and then it's up to you to decide what it means. Actually, double fault occurs because the SMEP supervised mode execution prevention does not allow you to use the user in signs in the kernel space. In other words, when you are in the kernel space, you cannot get access to the user space. And the only thing we can legitimately use are copy from user functions. And when the control flow is hijacked, this SMEP cuts off the attack I demonstrated to you the previous time. So the first thing that we can do is put our ROP chain into the kernel space rather than the user space. In that case, the SMAP will think that everything is fine because we're in the same kernel space. So we will flow the buffer with some holder, and everything else will be erased with our ROP chain and gadgets. This is the way it's going to look. The structure, again, is basically the same as compared to the previous exploit, but this is the way to bypass the SMAP.
Кстати, я забыл одну важную вещь.
Oh yeah, by the way, I missed one important thing. We have to make sure that these protection means are on. You just do the usual grep. Let's double check that the SMEP, SMAP are on. It's in the proc FS, and you can type in the SPU info. And as you can see, both SMEP and SMAP are on. We do the exploit, and everything is fine.
Последнее, о чем хочется...
And one last thing I want to cover, and I guess this is the most important part of my presentation, is that on a daily basis, we detect multiple vulnerabilities. I was talking about the Linux kernel, but other projects focus on that as well. And on a daily basis, guys crash KCTF, they use sysbots, they debug kernel bugs, and so on and so forth. But this is a code written by a man, and all these vulnerabilities are a human factor. In my case, this vulnerability can be debugged in the following way. You just need replace copy from user no fault with copy from user, and it's a safe function that double checks the size of the data fed from the user space to the end buffer. And if it's more than 32 bytes, then the process is killed and nothing is transferred. The account would be another way, but I think this one is safer. And the blue hats can use the kernel KC-Fi in the grep to test. I decided against going into detail because the kernel would require a recompilation, which is not always convenient, and it's not always a good idea if you're not an expert on that, but I still mention it. That brings me to the end of my presentation. Thank you so much for coming. If you have any questions, I'll be happy to take them. There was a question about the RSP. Would you please use the mic?
Да. Откуда мы взяли РСП?
Where did we get the RSP from? Was that the question?
Я понял.
Got it. Right. So that's a great question, by the way. Let me explain something. When we hijack the control flow, we cannot just throw the kernel out because we get access to the root. You have to restore it and go to the previous execution context. And I cheated a bit. Let me be honest about that. When I debugged the kernel and the entire project, I couldn't help but notice that my kernel module allocates the very same space every single time. And since I don't use KSLR for randomizing the kernel space, my RSP is always the same. It's identical regardless of the startup. So the RSP is hard-coded. It's a dirty trick, but it works. And you know, I used it for bypassing SMEP and SMAP. Thank you so much for your presentation. I have another question, if I may. In real exploits and in real vulnerabilities, in order to bypass the SMAP, you need to place the payload somewhere in the kernel space. But what do you do if you don't know the precise location? What do you do in that case? That's a good question. We can consider the use after free vulnerability, since the Stack Overflow is a simple attack, right? And you know, these vulnerabilities are not used, are almost not used anymore. As for the use after free the vulnerability, you can use the hip spray technique, and the hip spray technique it basically allows you to allocate lots of kernel objects of the same size as yours that you use for the use after free attack. And ultimately, if you use MSG and MSG, by the way, this is the guy who invented the hip spray with MSG. And in this way, you can control the use after free with the MSG technique to deploy the use after free attack. So you're saying calculate something and do the data leak. Exactly. In the MSG there are size fields, and if these size fields are affected, for instance, this is the use after free somewhere in the middle of the object, and you see the MSG size field there. You can change it for something huge, and you'll be able to read part of the kernel memory, and you'll be able to identify the location of the vulnerable object. So to sum up, SMAP bypassing is difficult because it requires the precise location of the vulnerable object. Exactly. The data leak is a must-have. In my case, it was not necessary because I just went manual by manual. But if you place the data that the attacker wants to get access to, for instance, a root chain, of course, for bypassing SMAP, you need to know the location. Cool. And I believe that the SMAP bypassing the cheater method is the simplest one I've ever seen. Exactly, because I wanted to simplify things for the newbies. Thank you so much.
Тут еще вопрос.
There is another question. Actually, I have two questions. The first one is as follows. There are two assumptions, switched off canary and switched off SLR. And in real conditions, the attack is going to be much more complicated because, well, as for canary, it's one thing, but SLR is a headache, is a real headache. And my second question is, well, in the next month, if I'm not in the past month, if I'm not mistaken, IOU link was a subsystem that was identified, and it allows you to move user space data into the kernel space. You can think about using it as an exploit. As for your first question, the stack canary could have been activated, and we could have tried to bypass the canary if you change the kernel module somewhat. But we were only talking about the write ability. However, if your function allows you to move data from the kernel space to the user space, in that way you could create an artificial vulnerability in the second function, and that will help you to do the data leak in the stack canary.
Хорошо, спасибо большое.
Right, thank you so much. If I may, well, your link is something that I want to comment on. There are thousands of ways to move data from the user space to the kernel space. Any system execution with a link to the buffer to the user space will move the data, and it will copy it from user. And the RU link does not differ much in that regard. But there are lots of bugs inherent in it, and that's why many Linux kernels manuals say that recommend that you switch it off if you don't use it. It's a very complex subsystem with lots of debugs, and the kernel CTF, it's a Google CTF to attack the Google links. They switched it off because they got sick and tired of pinging out the money. So any system execution that allows you to copy data into the kernel space, even if it's the file descriptor right, it'll do the same thing as the RU link.
И у Юринг не мапят напрямую те страницы, которые общие с юзерспейсом получаются. Это было бы немножко сильнее, потому что это позволяет писать память ядра во время того, как он исполняется для гунок, например.
У страничек же user-bit есть.
The user bit is available to pages. For instance, you have kernel pages, user bit, and SMEP does not work that way.
Я не знаю, делать ли оно так с его
Я не уверен, что так можно.
I'm not sure that you can do it for the IE ring, but ePPF works that way. So you have a JIT inside the kernel, and from the user space you inject a code into the kernel space, and this is so for that. And ePPF is recommended to be switched off for security reasons. It's off by default. There is a config that prevents a non-privileged user to execute ePPF. If you reconfigure the kernel, it will not work. And by the way, Yesterday, the Chinese talked about out of bounds in various file systems, and they used UPPF JIT spray to deploy their attack. It was a very interesting presentation. Watch the video.
Очень.
Сам рисовал.
Если загуглить ASCII art, там
Well, if you Google ASCII art, the very first hyperlink will send you to the PRJOK website. I don't know how to pronounce it, but you can generate different things. The spider web was something that I created. Thank you so much for your questions.